Okay, welcome back to chapter 25. Here we're going to be talking about variance, standard deviation, a little more about expectation of discrete random variables. So right away the book jumps in with some formulas. We saw in the previous video that the mean of a discrete random variable, the mean, sometimes called the expected value of it, can be calculated by taking each of the outcomes, multiplying them by their respective probabilities, and then adding those all up. Now we have also formulas for the variance of a discrete random variable as well as the standard deviation of a discrete random variable. I recommend not to jot down these formulas that appear before you, but actually to write them down as they appear in the formula book, if you're going to write them down at all, that is. Let's take a look at the formula book right now. So for starters, this first box, this is stuff we saw back in chapter 23. So this is the mean of a set of values, the variance and the standard deviation of a set of values, related to, but not the same as, the mean, the variance, the standard deviation of a discrete random variable. So that comes farther down. Okay, remember all these, our friends from chapter 24 are here. More chapter 24. And now we got down to the last three boxes. This is going to come in chapter 26. Don't worry about that. But these two boxes are going to show up in this and the next video. So here's our expected value for a discrete random variable. This is what we said it should be before. It's going to be the sum of each x value, each outcome, multiplied by the probability of that particular x value. This next formula, don't worry about it. This is for continuous random variables. We'll see that in chapter 26. They're together because they're both about expected value. Variance. This is kind of a general variance formula for random variables. And here we have a specific format for discrete random variables. And again, below we have continuous random variables. From these, the only way to calculate standard deviation is to take a square root of variance. That's fine. Peeking ahead to the end of this chapter, we're going to see the binomial distribution and the Poisson distribution. Those are two very, very special discrete random variable distributions, and they will have simplified special formulas to calculate their expected value and their variance. But more on that at a later time. Okay, let's just do some, and then we can talk more about these formulas as they show up. Okay, take a moment to read this. Pause, pause, pause. Okay, first thing I want to do here is make a table so I can see the probability distribution. Okay, so x sub I is going to represent the payout, and then down below we have the probability of that particular payout occurring. Okay, so we've got 0.0025 is the probability of the theft occurring, in which case they're paying out 20,000. 0.03 for loss, 8,000. I don't know how they determine the difference between those two, but whatever, that's not the point here. And then subtracting those two values from 1 gives us 0.9675 for them paying out nothing. Okay, so the question, how much should they charge to cover the ring so that their expected return is $100? Kind of had a problem very similar to this at the end of the last video about some carnival game. So let's figure out what the expected value is right now, and then we'll make sure they get $100 more than that. So we're going to start off by grabbing a calculator, because I don't want to do this in my head, and we're going to multiply 20,000 by 0.0025, and miraculously that comes out to be 50. And then we're going to do 8,000 times 0.03, and that ends up being 240, and then obviously 0 times whatever is 0. So right now, their expected payout is going to be 290. But they don't want their average payout to be any positive number. They want to be paying out negative values. In other words, they want to be making money on the average. So how much should they be charging? So if their expected return is 100, well, it's going to be, they have to cover the 290 plus 100 more. So they should be charging $390 for this insurance policy. Okay, next up, we're rolling a pair of dice again. We're going to let the random variable m be the larger of the two numbers that are shown. So, and if we have the same value, then it's just whatever the value is. So I guess m here is kind of standing for maximum. So for starters, we want to come up with a table. So again, along the top and left, we have the values that could be rolled, and then in the table itself, we have just the largest number. Okay, so now let's record the probability distribution of m. Here we are. We've done this a bunch of times before. Just count up how many 1s, 2s, 3s, 4s, 5s, and 6s there are. Jot down the probabilities. Okay, so there's our table. That's for part A. For this, such a fancy name, for the m distribution. Okay, so find the mode. Well, the mode here is definitely going to be 6. That's got the highest probability of occurring. Seems pretty obvious. Find the median. So we're going to go through this and figure out when we get to 50%. 50% would be 18 out of 36. The median is going to be 5. Since when we go 1, 2, 3, and 4 is only going to be 16 36ths. But when we add up 9, we get above 18 36. Okay, the mean value is going to be 1 times 1 36 plus 2 times 3 36 plus 3 times 5 36 plus 4 times 7 plus 5 times 9 plus 6 times 11. Add those all up, you've got yourself a mean. Ends up being like 4.47. And then finally the standard deviation. So the way we could do this with a formula is here I've copied the formula for variance from the data booklet exactly as it appears. Okay. Since we want the standard deviation, we know we need to take the square root of it. All right, and then we just have a notation change here because I'm too lazy to write this out, so I'm using the book's answers. Instead of x squared times probability of x equals x, we've got that instead. So we're using m sub I here instead of x. That's the same thing, whatever. And p sub I is just the probability. So then we go through for each of these, right? We would do. So it's going to be 1 squared times 1's probability plus 2 squared times the probability of 2 plus, and so on and so on and so on, all the way to 6 squared times the probability of 6. And then we would subtract away from this the average, the mean squared. So I guess that mean there that I had calculated that earlier, and I just wrote down the decimal of 4.47. Its exact value was 161 over 36. Okay, on a calculator, this gets us a value of about 1.40. Okay, but that process sucks. You don't want to do it that way. All right, let me show you a nicer way. And this nicer way is going to also get us the value for the mean, the 4.47 that we saw before, but if it was me calculating the mean, I would probably just do it this way. This doesn't really take that much time or effort. But for the standard deviation, I would absolutely use a spreadsheet on our calculator. And I'm sorry, just if I wanted to get this, I would, down here at the bottom, I would open up a new spreadsheet from right here. Okay, so what we're going to do is we're going to just enter in the information from our probability density table. So I've got my outcomes and my probabilities. I entered them in with denominators of 36. My calculator automatically simplified the fractions. Isn't technology beautiful? Okay, I'm labeling these outcome and probability so that they have names. Here we go. Over here, we did stuff like this back in chapter 23. So we're going to go to menu, statistics, stat calculation. It's a one variable stat calculation. I have only one list. Great. My X list is going to be outcomes. My frequency list is going to be probability. All right, so and that's telling me like the frequency with which those outcomes occur on average. Everything else I can ignore, hit OK. All right, what do we have over here? Check this out, X bar. Remember, that's the symbol, that's what the calculator is going to use for the mean. The IB is going to be using mu. Anyway, that's our average, 4.47. Awesome. Down below, we're going to find standard deviation. At first, that says it's undefined, but you may recall that's the wrong standard deviation. We're going to use this one. There it is, 1.40. Moving into section E, so some properties of expected value. The expected value of a constant should be a constant. It's pretty unlikely that you would ever have to think about that, but I suppose it's true. The the expected value of a constant multiplied by a random variable is that constant multiplied by the expected value of the random variable. That makes sense if you think about expected value in terms of like averages, right? If we take each of the values in a data set and we multiply them all by the same constant, that's the same as just taking their average and multiplying the average by that constant. And expected value is, it can distribute in a way. So the expected value of a of x plus b of x, if those were two different probability functions, that's equal to the expected value of a of x plus the expected value of b of x. These don't show up too often, but we'll see some simple examples here. Okay, and here are some very simple examples of each of those three. Okay, and then down below we've variance. There's nothing really new here. This is just stuff that was in the formula sheet before, right here. All right, let's do some stuff. We've got a probability density function. Let's find the mean, find the variance, and then find the standard deviation. Okay, the mean is very easy to calculate. I'm going to take each of the x values, multiply them by the probabilities, add them up. Done. The variance. We're going to use the formula that we just saw on the previous page now. Okay, we're going to first calculate the expected value of x squared, and then subtract from that the expected value of x squared. All right, so this is a little bit quicker, perhaps, than using this formula. This is the formula we kind of used in the previous example, right? Turns out we can use this formula here as well when it suits us, if it ends up being easier, which in this case it certainly is. So we've worked out what the expected value of x squared is. We just figured out what the expected value of x was, so we can square that, subtract, blah, blah, blah. There we go. That's the variance of x. Therefore, the standard deviation is going to be just the square root of that. Okay, well, I know I struggle with some of these problems and figuring out, gosh, what formula should I be using when? I think I don't know, experience, I think, is the key. I can't really give you a shortcut to know which one of the variance formulas makes sense to use in a particular problem without just trying and getting used to it. I'm sorry. Okay, so here's some more facts for you up at the top. So, well, we just discussed that expected value kind of distributes. Okay, so this first fact is coming straight from 2 slides back. Variance, however, does not distribute. Think about this in terms of standard deviation, though. We kind of talked about this back in chapter 23. If we were to take a random variable and multiply it by a number and then add another number to it, right? How would that change? If we took a set of data, like a set of numbers, I should say, if we multiplied them all by a constant and then added a constant to them, how would that change the average value, right? Well, the average value we'd be multiplying by that same constant, and then we'd still be adding that other number. That's kind of what we see here. Whereas the standard deviation, if we add a constant to every number in a data set, the standard deviation does not change, right? Because they're all shifting together, so their spread is not being affected. However, if we multiply every number by a constant, then the standard deviation would also multiply by that constant. If the standard deviation is multiplying by a constant, then the variance is going to be multiplied by the square of that constant. So that's what we got going on up here. So down below, we have a question which I meant to hide the answers to. Oh well. We've got a particular distribution of a random variable x. It has a mean of 8.1 and a standard deviation of 2.37. We have a new random variable y, which is 4x minus 7. We want to find its mean and its standard deviation. So the mean, first of all, is going to be, here we go. The mean is just going to be 4 times the mean or the expected value of x, and then minus 7 from that. The variance is just going to be, well, excuse me, the standard deviation would simply be 4 times the standard deviation of x, which means that our variance is going to be 16 times the variance of x times the standard deviation of x squared. So we got 16 times whatever 2.37 squared is. Taking the square root then, because the question actually asks, sorry, for the standard deviation, we get that, 9.48. As I said back in chapter 23, I believe, standard deviation is like generally much more useful than variance, yet for whatever reason, the IB gives us a lot of formulas and information about variance. Like I would never have written this in the book. I would have written the standard deviation of ax plus b is equal to a times the standard deviation of x. They decided to give it to you in variance and then make you mentally work with it. Anyway, let's continue. All right, marsupials. This is exactly as I imagine them in their natural habitat. All right, here we've got another function giving us the probability distribution. So let's work out what those probabilities are. Here we go. Putting in 0 through 8 for x, we get these probabilities come out. Notice the symmetry here, and that is to be expected since we have x squared minus 8x. We've got this parabola happening here. The vertex of that parabola is when x is equal to 4, and that's exactly the center of our kind of symmetry here. I don't know if that's important, but it just pops out at me. Anyway, finding the constant a, well, we're going to add up all these probabilities, and we're going to set them equal to 1. Okay, it ends up being -1 over 84. Strange number to pop out, but so it is. B and C, we want to find the expected value as well as the standard deviation. As we saw in previous examples, we could either use the formulas. Oh my gosh, there they are. Let me make that a little smaller. So we can use the formulas to work out what they are, or we could also go to our calculator, put in one column for 0, 1, 2, 3, 4, 5, 6, 7, 8, put in a second column for what the probabilities are. So we'll have to fill in what A is for each of those, and then you could do a one variable stats, and it'll tell you what everything is. All right, there's nothing to that. Next one, a box has 10 almonds. We're replacing 3 without replacement. X is going to be the number of bitter almonds. Find the probability distribution. Okay. We could attack this with a tree diagram, or we can use combinations to figure out what the probabilities of choosing 0, 1, or 2 bitter almonds should be. We could not have 3 bitter almonds, of course, because there are only 2 in total which are bitter. So that's why we're only going to do 0, 1, or 2. So we calculate those probabilities, throw it into a table. Awesome. From there, same thing as before. If we want to find the mean and the standard deviation of x, we're either using the formulas straight from this table here, or we're going to go to our calculator and enter them in there. I'm not going to go through it this time. I think you've got the idea. Okay, last one. Back to a table. Here we got to find 2 values from it. At first glance, you might think, oh, there's going to be a system of equations we need to solve since there's 2 variables here. It ends up not being that bad in this case because since we know the expected value is equal to 0.9, calculating the expected value from the table, A is matched up with a value of 0. So that's just going to drop out. So it's just going to be negative 0.1 plus 0.3 plus 2b. So from there, we can work out what b has to be, right? Because this is going to be 0.7 over 2 is b, or 0.35. Once we know what b is, we can then figure out what a is, because those 4 probabilities have to add up to 1, so that a should be equal to 0.25. And finally, from there, same deal, either using formulas or getting to the calculator to work out with a spreadsheet to work out what the variance is for part B. Once again, I'm not going to do that. So, main takeaways from this video. All right, we got some new formulas that we've got to be aware of. Okay, there have been questions on paper 1 where you needed to be able to use those formulas. So just know that they're there. Spreadsheets. Definitely want to be comfortable using those. If you are still using a TI-84 or any other calculator model, please speak to me in private, or if you are not a student in my class, talk to your teacher in private, or I don't know, leave a comment down below, and someone will help you out. Because they're definitely going to be very helpful for solving a bunch of these problems. All right, so that's it for generic probability distributions. Okay, we've seen quite a bit in sections A through E. Again, even sections D and E, like fairly foundational. The real exciting part, and where most of the questions from this chapter come from, are sections F and G. But those we'll have to wait for until another day, or at least another video. Until then, I bid you farewell.